Building on our definition of a graph in terms of being a set of nodes and a set of edges which connect either two of those nodes or a node to itself, we say that the graph is a tree if it's a non-empty, undirected graph which is connected and has no circuits. So connected means that any node, there exists a path to any other node, and no circuits means that there's no two different ways to get between any two nodes. Now, keeping the horticultural analogies going, we say that a leaf in a tree is a node with degree 1. So what that means is there is only one edge coming into and therefore out of it. So those are the end points, so to speak, of each branch of this tree. And then with the tree-based analogies, we often say that if we have a number of trees, which may be unconnected to each other, that collection of trees is a forest. So each of these three trees here is, well, each of these three trees is a tree, and the union of these is a forest of those three trees. Now that we have our definition of what graphically a tree is, there's a few properties that we can prove. If I've got a tree with n nodes, it has to have n minus 1 edges. And again, this one I've drawn here is a 6-node, 5-edge graph. Well, let's prove this. Well, clearly it's true if I've got one node, because if I have one node, that is a tree. It's connected because the node is the node, it's the whole tree. There's no cycles, there's no edges going round to anything. It can't have any other edges, so thus it is a tree. It's the simplest trivial tree. So that proves our base case in a sort of inductive argument. But let's assume it's true for n equals k nodes, and we want to show therefore that it's true for n equals k plus 1 nodes. And that shows by induction, if it's true for one node, then it's true for 2, therefore 3, therefore 4, therefore 5, and so on. So our inductive proof just says, well, what happens when I add one more node to the tree? I start with it saying it's true for a graph with k nodes, and therefore k minus 1 edges. So if I add one more node, the k plus 1th node, well, in order to keep it as a tree, my new node has to be connected to the existing graph. So I need at least one edge, otherwise my new node is not connected, thus not a tree. So there, I've just visualized it in the top right. But what happens if I add more than one edge? So I need at least one edge to keep it connected, but if I add more than one edge, then I will definitely create a circuit, because either my new edge loops the new node to the new node, in which case it's created a circuit in the form of a loop, or it connects two existing nodes of the graph. And of course, if I do that, then I've created a different path between those two nodes it connects. Because the original graph was a tree, so there was a path between the two nodes that I just joined via my new node. And now there's a second path. So therefore, I've created a circuit. So that isn't possible. We also have an equivalent definition of a tree, And this says that a graph is a tree if and only if it's connected, but removing any single edge would make it unconnected. And we do that by showing that if we start with a graph G and we remove any single edge, the resulting graph G prime, which is G with this one edge removed, can't be connected. Well, if we think about this, G is a tree, so it contains no circuits. So let's say that the edge that we choose to remove is the edge which joins node X to node Y. So this gives us two possibilities. Now either G prime is disconnected because the link between X and Y has been broken, has split this into two different subgraphs, the graph that contains X and the graph that contains Y, but they're not connected. Or the other option is that they are still connected, but if they're still connected, then there's another path from X to Y. So if there's another path from X to Y, then there were two different paths from X to Y in G, so G wasn't a tree in the first place. Similarly, we can say that if G is a connected graph which does contain a circuit, removing an edge from the graph won't always make it disconnected. Maybe it will if the edge I remove is not part of the circuit. But of course, if I remove the edge from the part of the graph which is the circuit, by definition, a circuit has more than one path between two nodes. So if I remove one edge, I could just sort of go the other way around the circuit, the one remaining path